Good day, everyone. My name is Andre Turin. I'm the Technical Director for DuRock Alfacing, and I'm here today to speak to you about the use of Eaves as an exterior wall retrofit solution. So without further ado, I would like to get into the presentation itself. So the first thing I want to do is give you a very short, brief history of Eaves for those of you that are not intimately familiar with the systems. By the way, first and foremost, the acronym Eaves stands for Exterior Insulation Finish Systems. And the one thing I would like everyone here to know is that the precursor to Eaves was first developed in Europe post-World War II as a means to insulate buildings. So as everyone can appreciate, they had gone through a war and they had buildings that, number one, were in need of a lot of significant repair, as you can imagine. And also, for those of you, if you can appreciate going back that far, buildings at that time were for the most part not insulated at all. And if they were insulated, they were very poorly insulated by today's standard. So hence the need for Eaves, and it came to be, and we're talking now circa 1950s Europe. So let's fast forward about 50 years to the late 1960s, I would say, when, like everything else, before Eaves came to Canada, it went to the United States. Eaves has already a 50-year proven track record in the US. Here in Canada, it's already been in use for over 40 years. Now, when Eaves came to North America, it was immediately transformed as a cladding solution for new construction, because that's primarily what has been built over the past 50 years in both Canada and the States. But don't forget that the origins of the system itself came from retrofit. Because if you can imagine, again, going back to 1950s Europe, there were many buildings at that time that were in need of some sort of retrofit. And that's where it all began. Even though we have never had a war on our shores, and hopefully we never do, we do have something in common with those post-World War II buildings in Europe. We now here in Canada have an aging stock of buildings that are themselves in need of, number one, energy upgrades, because once again, we have many buildings here that are either not insulated or, once again, by today's standards, poorly insulated. And of course, we have buildings that are in need of a facelift. They need a new appearance. They need to be refreshened. And that is where Eaves really shines. So fast forward to today. Eaves today is a completely codified solution. It is an acceptable solution in accordance with not only the National Building Code of Canada, but also with our provincial codes. So in a nutshell, Eaves are, simply put, number one, they are continuous insulation. I will expand more on that term later on in the presentation. But first and foremost, Eaves are rainscreen cladding. For those of you familiar with the rainscreen principle, we're talking about a cladding that is separated from the building. It has a drained airspace in between the cladding and the backup wall, and it also has both a first plane of protection and a second plane of protection as it regards rain penetration. So the first thing I'd like to talk about, starting from the outermost layer of the system itself, moving inward, we start off with the lamina. The lamina is the outer skin. It would be the coatings that go on the face of the thermal insulation board. That lamina is the first plane of protection, or to use code language, first plane of protection from precipitation. The lamina also has a dual function. Because for the most part, the insulation in Eaves systems is a combustible foamed plastic, specifically more often than not polystyrene insulation, that insulation must also be protected from fire. So that lamina is keeping the rain out. Rainwater does not penetrate that lamina. That lamina is also protecting the underlying insulation from fire. As I mentioned, the insulation most commonly used is the expanded polystyrene. I'm going to touch on some other insulation materials that can and are used with EIFS systems. The one thing to remember that all EIFS have in common, and that is the insulation component itself. EIFS is not EIFS without the insulation. It is the backbone of every EIFS system, and it is what EIFS has been about since its inception, going back to Europe post-World War II. And that's where this continuous insulation aspect comes into play. Next thing that we have, again, following the rainscreen principle, is the drained airspace. So you now have inboard of the cladding element, separating the cladding from the backup wall, is a drained airspace. And last but not least, the water-resistive barrier, which would constitute the second plane of protection, to use code language once again, and any and all water must and is stopped by that barrier. So that's the inner boundary, if you will, that stops all rainwater. So in a nutshell, that is what EIFS are. The one thing that I'd like to state just very briefly is what EIFS are not. EIFS are commonly confused with stucco. From a building science and from a building code perspective, EIFS and stucco could not be any more different. I've just spelled out to you here very briefly the basic elements of an EIFS system. For those of you familiar with stucco, if you were to look into our building codes, for example, what you would find is some sort of sand and cement render, typically reinforced with some sort of metal or wire mesh. There is no insulation component to stucco, aside from all of the other elements that I've just mentioned. So just to clarify, EIFS is not stucco, although the two terms are quite often used interchangeably. So to put this into an illustration perspective, this is your garden variety EIFS, the EIFS system that I just spoke of. You see in that illustration in front of you right now, what you can see are some of the substrates that EIFS is more commonly applied to, starting with your CMU, your concrete block, then you have cast in place concrete, you have masonry brick in the middle, and then on the far end, what you see there are sheathing boards over framing. That framing could be either wood or steel. So when we talk about new construction, we're typically talking about frame construction with a sheathing board on top of it, because that's how we most commonly build here in North America. But of course, getting back to our retrofit roots, when we're talking about mass walls, specifically or especially if those walls happen to be brick, that is once again where these systems are ideally suited. All it is dependent upon, of course, especially when going over existing brick, is making sure that the brick is of a suitable condition. Its condition should be assessed by a professional, looking for things like, is it structurally sound? Is it spalling, etc., etc. Now, to look at the system that you see on the illustration, just to go back to the various layers that I just laid out in the last slide, you see a mauve colored coating that appears to be applied over the substrate, over all of the substrates there, regardless of which one it is. That would be your first coat WRB, or water resistant barrier. Once again, an integral component of every EIFS system. EIFS is not EIFS, not only without that insulation component, but also the WRB. The WRB in EIFS is an integral component of the system. EIFS are not installed over your common sheathing membranes like many other claddings. EIFS includes its own WRB. So we start off with the WRB, then you can see a gray coating there between that WRB and the insulation. That would be your adhesive. EIFS, for the most part, are adhesively fastened. There are areas or instances where EIFS must be mechanically fastened, but that's depending on several other conditions. For the most part, your standardized EIFS that are recognized in the building code are adhered systems. You can't see from this illustration, but trust me, on the backside of that insulation, there is a drained airspace. Again, a basic code requirement. And then that lamina that I spoke of, that outer skin, the layers of coatings that go on the exterior face. If you look on the insulation board itself, what you're going to see first is a gray coating. That would be your base coat, which is integrally reinforced with a fiberglass mesh, most commonly, and then a decorative finish applied on top of that. So that's your garden variety EIFS. That's your standard basic EIFS that is code recognized today, both, like I said, both in our provincial as well as national codes. Going into those codes back some 6 years ago in 2015, to be exact. So when it comes to performance, EIFS is not just a cladding, and it is not just there for aesthetic purposes. It actually has several functions to within the context of the building code. So I'm talking about environmental separation. For those of you familiar with that term, what we are talking about is something that separates the conditioned indoor space from the outdoors. In other words, keeps the rain out, keeps the heat in, at least in the wintertime. In the summer, it does the opposite. It has to control air leakage, control condensation. So I'm now talking about vapor permeance and the like. And last but not least, resist fire. So any element of an exterior wall or part of the building envelope must control all of those elements, and EIFS addresses each and every one of those as it relates to the related building code requirement. I am now going to expand a little further on each of those points individually. So let's start off with rain, protection from precipitation. For those of you, in case some of you are familiar with code, as I mentioned a minute ago, EIFS officially went into, or formally went into, our building codes in 2015, both at the national level and at the provincial level. And over the course of the past 6 years, most, if not all, of the other provinces have adopted EIFS into their perspective or respective codes as well. So there is a standard for EIFS that is recognized in these codes, and it is CANULC S716.1. It is a materials test standard, a standard that most, if not all, of the EIFS systems that are currently marketed in Canada comply with, and it is the most basic component or element for EIFS meeting code. Now, there are many other standards or code requirements that would apply equally to EIFS, but as far as getting into specific code requirements, this is the only standard I'm going to mention or get into any depth in relation to here today. And the reason that I'm going to do that is because if I were to get into either building codes or energy codes, talking about provincial, especially provincial codes, we have a problem in that there is a difference between some of the provincial codes and the national code as far as how they address different aspects, performance attributes of claddings. So rather than confuse and alienate people by doing a deep dive into those aspects, I'm just going to touch on them from a macro level more briefly. If anyone wishes to get information more specific or pertinent to their particular province, or for that matter, when we talk about energy codes, we're now even talking about climatic zones within provinces. So if anyone wants further information on any of those related aspects, I would invite people to contact me after the presentation, and I will gladly address any of those type of issues. So I've mentioned here the standard briefly. I just want to touch on some of the tests that are contained within that standard. That standard is the benchmark for all EIFS in Canada. It is one of the most stringent standards that applies to any cladding material, and that is because, as I mentioned several times already, EIFS just went into the building codes relatively recently. I'm speaking 2015 to be exact. And though that standard includes several different test requirements. First and foremost, environmental cycling or durability. That includes freeze-thaw cycling, demonstrating that the systems can withstand the Canadian climate. There is also a drainage capacity test in that standard, which is highly regarded as perhaps the most stringent drainage test in perhaps all of North America, definitely here in Canada, but perhaps all of North America. A very difficult test to pass. Very few other cladding materials would pass that test if they were ever to be subjected to it. And of course, any EIFS system that meets the intent of our building code must first and foremost meet that requirement. Obviously, wind load resistance, basic National Building Code requirement, especially when EIFS is used on large and tall buildings where wind load resistance becomes more of an important factor. So EIFS are extensively tested for that property as well. And last but not least, impact resistance. EIFS is able to withstand whatever impact it may be subjected to. So just a very brief overview of the testing that all EIFS in Canada are subjected to. So moving right along, give me 1 second, please. I'm now going to talk a little bit about thermal performance. So we're talking about R values and U values for those of you familiar with code. So I mentioned at the very outset of the presentation, I talked about a term, something called continuous insulation, or CI for short. That is a codified term, and it applies to any insulation that is continuous across structural members. And it just so happens that EIFS is and always has been the very epitome of continuous insulation. That is what the EIFS industry has been about from day one. When we talk about insulation that is continuous across structural members, of course, the easiest way for me to explain that is to say that any insulation that is within a stud cavity is not continuous. So any insulation that bypasses that framing would be continuous. And the reason why continuous insulation is so important from a thermal perspective is because any insulation that is put inside a stud cavity is subject to thermal bridging. That thermal bridging can greatly reduce the thermal effectiveness of that insulation. Just to put that farther into perspective, any insulation that is inside a wood stud cavity, you're looking at probably around a 25% loss in effective thermal resistance because of the wood framing. You put any insulation, even the best insulating material in the world, you put that inside a steel stud assembly, and you are now losing upwards of 50% of the effective insulating value of that material. So again, that's why continuous insulation is so valued from a thermal performance perspective. So when we talk about the thermal bridging, EIFS for the most part is not subject to thermal bridging, or if it is, very minimal compared to other alternatives. For the most part, as I mentioned at the outset, EIFS are adhered systems, so there are no thermal bridges going through the insulation itself. When you look at competing alternatives, many of them have girts, shelf angles, exposed floor slabs. All of those elements constitute huge thermal bridges, which definitely very negatively affect the thermal performance of any cladding solution that is impacted by those measures. EIFS assemblies have been tested by various manufacturers in the industry to demonstrate that they do deliver and can deliver the full thermal performance of the insulating material contained within them. In other words, that there is no loss in thermal performance using EIFS. And if there is, it's minute in comparison to the losses attributable to other alternatives. Most manufacturers, if not all manufacturers, have done this testing. And of course, the testing may vary by manufacturer and by system and it's best to consult the individual manufacturers for the results of their own proprietary testing in that regard. The next aspect that I would like to touch on is air leakage. Another codified element, code requirement of any exterior assembly is that it control air leakage, first and foremost. So the WRBs, or water resistant barriers, that I talked about with Eaves, that is, if you recall, the second plane of protection against rain penetration, it is on the backup, or it's applied to the supporting wall before the Eaves system is installed. Those materials characteristically satisfy the air leakage requirement in our building codes as it relates to air barrier materials, and therefore Eaves WRBs automatically qualify as air barrier materials. And one of the reasons why air leakage is so important is that it has been said that air leakage alone accounts for as much as 30% of the loss of energy out of buildings. Okay, so it's not just a matter of insulating them well, you've got to control the air leakage. And as I mentioned, the materials, the WRB materials, are essentially air barriers in and of themselves. And it just so happens that by code, Eaves WRBs must be continuous, which is something that they have in common with air barriers. Air barriers also by code must be continuous. So what I'm trying, what I'm trying to say here is that Eaves WRBs are ideally suited to function as the air barrier for the opaque wall assembly. They are performing that function whether people designate them as such or not. All that needs to be done is that they have to be someone has to maintain the continuity of that membrane in order to make the building airtight. So now I'd like to move on to condensation control. Now, on the topic of condensation control, we're now talking about vapor permeance and vapor diffusion. Essentially, what all of our codes say, and they all pretty much say the same thing, they say that we have to put vapor barriers on the warm side of assemblies to control vapor diffusion from the interior so as to minimize the accumulation of condensation in the assembly. That's a long-winded way of saying that what we have to do, because of the way that we build, or typically build throughout all of North America, and that is by using, for the most part, moisture-sensitive building materials within our walls. I'm talking about frame construction, be it wood or be it steel. I'm talking about sheathing, be it wood-based or be it gypsum. All of those materials have one thing in common, and they are all moisture sensitive, and that is that they can be severely impacted by long-term exposure to wetting. So what the codes rightfully so says, put a vapor barrier on the inside so that the humid indoor air can't get into the wall assembly and condense, in other words, turn into liquid water, and then cause all sorts of nasty things to happen. And as long as you have a properly functioning vapor barrier, it does deal with that issue quite well. Because don't forget, the dew point temperature of the indoor air is falling within that structural wall, unless, of course, there's something called exterior insulation on the outside. It is generally accepted or understood from a building science perspective that the best way to insulate any building is to put insulation on the outside. Because one, you've got that continuous insulation that I spoke of earlier, free of the thermal bridging. And not only that, you are bringing the dew point outside by doing so. So what I'm talking about when I say dew point, it's the temperature at which vapor in the air will condense on a surface. It is something that we don't want happening within our walls, as I mentioned a second ago. And by putting insulation on the exterior, by putting enough insulation, we can now bring that dew point from the interior of the wall assembly to the exterior so that the air within the wall cavity itself never gets cold enough for condensation to happen in the first place. That's the best way to prevent any condensation related issues, putting as much insulation as is necessary. Now, when it comes to especially existing buildings, someone should do a comprehensive analysis of that entire wall assembly, both the existing assembly and what is being proposed as far as a retrofit is concerned, to make sure that the right strategy is met for that particular building and for that particular wall, to ensure, once again, that water cannot condense within its walls. The last of the, I guess, code-related issues that I wanted to touch on today, of course, is fire protection. So when we talk about EIFS with expanded polystyrene, as I mentioned, the most common insulating material used with EIFS is expanded polystyrene. It is a combustible foam plastic, and in accordance with code, it must be protected from fire, especially when it is used on large buildings. And by large buildings, I am referring to, number one, any building that is over 3 stories in height, and any building that is required to be of non-combustible construction. The use of expanded polystyrene on those buildings must be fire tested. Again, I'm not going to do a deep dive here into those code requirements because they do vary by province. The only thing I wanted to say is that the code is replete with exemptions, and there are exemptions permitting the use of expanded polystyrene, or I should say combustible foam plastics, on the exterior walls of buildings. For those of you familiar, there are two, in particular, there are 2 fire tests that apply to EIFS within the context of our building codes. Those tests are CAN-ULC S134 and CAN-ULC S101. And for the most part, the manufacturers in the industry here in Canada have tested their respective systems to those requirements. And that's why those systems are permitted for use on those buildings. There's another area where the use of EPS, expanded polystyrene, is subject to limitation, and that comes down to something called spatial separation. So we're now talking about limiting distances. We are now talking about specific walls of buildings, not the buildings per se as a whole, but a specific wall dependent upon how big that wall is, how close that wall is to the property line, what the occupancy or use is of the building, are all determining factors as to whether A, there is a fire test required for that particular use, or B, whether the codes preclude the use of that insulation on that wall assembly altogether. So again, I'm not going to do a deep dive into what those specific requirements are because they vary by province. Suffice to say that there are definite requirements in place which any professional designer should be aware of. I'm talking now your architects and engineers that would design your retrofit work. The one thing that I haven't touched on in any great detail thus far is the other insulating material that can and is used with EIFS systems. And I'm talking now specifically about mineral wool insulation. As compared to polystyrene insulation, mineral wool, for the most part, is non-combustible. So now EIFS systems that use mineral wool themselves now are non-combustible cladding, whereas any EIFS system using polystyrene is considered, as far as the code is concerned, combustible cladding. And of course, when we use the mineral wool in a non-combustible cladding solution, that is permitted for use in accordance with our codes, once again, on all buildings and on all walls. There is no limitation based on spatial separation or other. So those are the basics of the fire protection elements as they relate to EIFS. Now I'd like to move into something a little different direction here. Now that I have covered the basic performance requirements or functions that the envelope must perform in terms of environmental separation, I've touched briefly on rain, heat, air, vapor, and fire. Now I'd like to move on into a study that the Eaves Council of Canada commissioned over the past several years. It was conducted by RDH. Some of you, I would hope that many of you are familiar with RDH. They are one of the most respected consulting engineer firms in our country. And they did a comprehensive study that concluded early in 2020. So it's about a year ago that they finished the study. The study included two essential elements. It was a life cycle costing study and a thermal performance study. So it looked at both aspects of construction in general across Canada. And what it was doing, the purpose of the study was to compare alternative wall cladding options, the most commonly used ones, once again, throughout the country. The study compared common cladding alternatives for two building archetypes in 4 climate zones over a 50-year period. So once again, a very comprehensive study looking at several different cladding options, 2 building archetypes, 4 climate zones, and 50 years. So the life cycle cost part of it that they did included everything from the initial construction cost to the energy use that the building would use throughout its life, including maintenance and repair costs. So it had both elements of construction cost and operating costs, once again, over a 50-year period. So the 2 building archetypes, the first one was your 6-story wood building. And once again, they looked at the most commonly used claddings on that building archetype, which would be Eaves, of course, with its EPS or polystyrene insulation, brick veneer, and fiber cement cladding. So those were the 3 claddings for comparison purposes on the 6-story wood building. They also looked at a 12-story concrete structure that had steel stud infill. And once again, it was Eaves with polystyrene insulation as one of the claddings studied. They also looked at, once again, brick veneer, commonly used both in the wood building and on the concrete structure. And they changed, 2 of the claddings changed for this study, or I should say for the 12-story building, and that is looking at precast and aluminum composite in place of fiber cement. So fiber cement being more common in the 6-story wood scenario, precast concrete and aluminum composite more commonplace in the 12-story concrete building. The 4 cities that they chose for the study were Vancouver, Calgary, Toronto, and Montreal. So 4 cities from 4 different provinces. Not only 4 different provinces, we have 4 different energy codes. Each province has its own energy code, and don't forget, you also have different climatic zones within each of the provinces. So all of the wall assemblies that were studied here were designed to comply with the current energy code requirements of the respective province. So again, when I said very comprehensive, we're talking about several different cladding options, 2 different building archetypes, 4 cities in 4 provinces, and 4 different energy codes, all over a 50-year period. What did RDH conclude at the end of that study? Number 1, Eaves was the most economical as far as construction cost, first and foremost. Just looking at construction. When we talk about maintenance and repair, Eaves was less costly than all of the other claddings with the exception of the brick veneer. the brick veneer was the most cost effective from a maintenance and repair perspective only. And when they looked at the composite, at the overall study, the 50-year cradle to grave, if you will, including everything from construction cost to operating cost, the Eaves had the lowest life cycle cost. Again, these are all wall assemblies that delivered the same thermal performance, meeting the respective requirements or the minimum requirements of the respective energy code of the city in which the buildings were located. Very comprehensive study, available to anyone who would like to review it in greater depth. It's publicly available through the Eaves Council of Canada. So enough about that. I would like now to move into a few buzzwords that we hear quite often. The first one being, of course, sustainability. It is a term that is being used more and more often. So I think it's only appropriate that we have a good understanding of how it relates to our built environment. So the first thing that I wanted to start off is just mentioning, what is sustainable development? Well, in a nutshell, sustainable development meets the needs of the present without compromising the ability to meet the needs of the future. Another way to say that is to say that what we've been building over the last 100 years is not very sustainable. Okay, because I'm sure everyone that's here watching today is well aware of what's happening in regards to climate change, and that if we continue building the way we are not going to have a very rosy future. So we've got to change the way that we build. We've got to make buildings more sustainable. So as it relates, especially now, to put it in the context of construction and buildings, when we're talking about sustainable design, it's all about reducing the consumption of non-renewable energy, in other words, fossil fuels. And it's also, of course, about reducing greenhouse gas emissions, or in other words, reducing our carbon footprint. So that's what sustainability is all about. And I hope everyone here can appreciate that well-insulated, airtight buildings are themselves sustainable. Okay, that is the key to sustainability, to reducing how much energy we have to burn to heat and cool our buildings, is by insulating them and making them airtight. Another buzzword that we hear quite often now, and especially more and more so these days than ever, and that is resiliency. It's related to sustainability, but it's a little bit of a different concept. Resiliency is the capacity of a building to function under extreme conditions, such as those attributable to climate change. So the few things that we do know about climate change is that it's happening, and what it's doing is causing severe weather events, which are becoming increasingly more severe and more frequent. So buildings have to be resilient. In other words, people have to be able to remain in those buildings when these events happen. Okay, right now, if we were to look at a power outage on a building in downtown Toronto in the dead of winter, it's a matter of hours before the occupants have to find somewhere else to live. Making buildings resilient could expand that matter of hours into days. That is the difference between people being able to stay put and people having to move, perhaps to another city altogether, depending on the extent of the power outage. If climate change is allowed to continue at its current pace, these extreme weather events will become even more severe. Will become even more severe and more extreme. So what we want at the end of the day are to have resilient, sustainable buildings. That is the best way to combat this thing, this animal called climate change. That brings me to the next topic that I wanted to touch on, which is something called passive design. Once again, I go back to some of the terms that I used when I was talking about sustainability. When we talk about passive design, the cornerstone of passive design, once again, continuously insulated airtight buildings. Again, whether the insulation or the air barrier on the buildings are EIFS or not, that is the best way to combat climate change, okay, and make buildings sustainable at the same time. You can't talk about passive design without talking about passive house. Passive house is, for those of you not familiar with it, it is an internationally recognized science-based energy standard whose goal is to significantly reduce energy consumption in buildings. For those of you familiar with the standard, it is one of the most stringent, if not the most stringent standard on the earth as it relates to energy efficiency. The energy levels that a building must meet in order to qualify as a passive house are almost, I don't want to say unattainable, but almost. Excuse me 1 second. The reason I say that is because what I want to bring to everyone's attention here is that we have this passive house standard, which is a very difficult standard to achieve from a building perspective. Mind you, the standard has been around now for many, many years, and there are many buildings throughout the world that have been designed and built to that standard. And for those of you that are thinking that maybe this standard is too stringent or too difficult to be met, the one thing that I'd like to put out there is don't be surprised if 10 years from now, that standard becomes the minimum standard in accordance with our energy codes. So that's how quickly this ball is moving from what today is considered best practice. Tomorrow will be minimum standard. So the sooner that everyone can embrace this technology, the better everyone off will be. On this note of passive design and passive house in particular, I'm going to do a very brief case study of a building in Hamilton, Ontario. The building is called the Ken Soble Tower. Some of you may have heard about it. It was recently retrofit. It was a complete retrofit, including, of course, the exterior of the exterior walls as well. And it also just happens to be the first passive house high-rise retrofit in all of North America. So it was quite an achievement. Just to give you a little bit of background on the building was originally built in 1967. It had been, I guess, abandoned for a number of years when the city of Hamilton, the owner, City Housing Hamilton, decided that they either A, had to knock it down, or B, renovate it. It's an 18-story structure. And at the end of the day, they decided that it would be more cost-effective to renovate that building and to bring it up to today's code standards, and even beyond, I should say, rather than going and building a new one. It was a fraction of the cost. The only thing that ended up remaining of that building was the structure itself. Because that building was abandoned, they pretty much gutted the interior of the building entirely. And the retrofit included every energy-related aspect of the building, going from mechanical to electrical to plumbing to life safety, and of course the building envelope itself. So this retrofit, it's a little unique in that they were able to do a complete retrofit and not just restricted to certain elements or aspects of the building because they would have had it been occupied at the time. But this building was unoccupied at the time of the retrofit. And that's why they were able to do as extensive a retrofit as they did on the building. So as far as the exterior is concerned, the envelope, the overclad, if you will, they used the non-combustible EIFS, that is the EIFS with the mineral wool insulation. They went with a full 6-inch insulation, and the system was installed right over the existing brick on the building. So it's pretty much the system that you see illustrated there. It has your WRB, your water resistant barrier, that was applied directly to the brick. That also served as the air barrier for the wall assembly, making the building airtight. And then the rest of the system went on top, starting with the 6-inch insulation, and then of course that lamina, the outer skin, the decorative finish. It's important to note that this building was done over 2 construction seasons. The air barrier, as you see with the photograph in front of you now, was done in 2019. And as you can see, it was done without tarping and supplementary heat. In other words, it was done within 1 construction season. They started in the spring and finished in the fall. So the entire building was first treated with a liquid applied air barrier over the entire building. That was year 1, 2019. Fast forward to 2020, the Eaves system went on, the cladding. Again, the entire 18 stories inside 1 construction season. As you can imagine, that building being completely retrofit, inclusive of all of its systems, that is a very energy efficient building, very sustainable, very resilient, to the point that it takes very little energy to heat and cool the building, and people will be able to stay in that building for days rather than hours in the event of a power outage. So the Ken Soble Tower now stands as a fitting example of a future-proof, well-insulated, sustainable, resilient, energy-efficient, airtight, safe, comfortable, affordable, valuable asset that is more than able to withstand climate change and counteract it. So when I'm talking about withstanding climate change, we're talking about resiliency. When I talk about counteracting climate change, I am talking about sustainability. And that is where we are going to see all of our construction, whether it be retrofit or new construction. This is the future of everything that we do in this country. The last thing I wanted to touch on today is in relation to aesthetics. As I mentioned at the outset, Eaves is not stucco. From a building perspective, from a building code perspective, or from a building science perspective, Eaves and stucco could not be any more different. Unfortunately or fortunately, they do sometimes resemble one another in finished appearance, but that's where the resemblances end. Eaves does not necessarily have to look like stucco. It can look like many other things. Number one, when it comes to color, Eaves is available in infinite colors. For the most part, the finishes are integrally pigmented, much like paint. So Eaves finishes are available in any color under the sun. There are a multitude of textures depending upon client preference. And Eaves can simulate most, if not all, commercially available building materials like brick, stone, and granite. And then, of course, one of the advantages of Eaves is dressing it up even further through the use of decorative moldings. I'm talking about cornices, keystones, sills, bands, etc., etc. And then, of course, making use of aesthetic reveals to break up wall areas so that you don't have these huge monolithic expanses. And that can once again, further enhance the appearance of any building clad with Eaves. These couple of buildings are quite interesting. So when we talk about color, That's just an example of what one designer decided to do with Eaves. Instead of having a monolithic look, just to help you understand where they came up with this color concept. These two buildings, by the way, happen to be in Japan. They're not in Canada. But that is Eaves on the exterior. This was a retrofit done, oh, God, I don't know, I'm going to guess somewhere around maybe 15 years ago. And the reason why the owners chose that color scheme, this is a resort that is open year round. So they wanted one building to represent winter and one building to represent summer. Just something that people may wish to consider. When I talked about those architectural profiles and shapes and reveals, again, you'll notice here, we only have one color, but we have a great extent of detail on the building. Once again, something that Eaves easily affords itself to for building owners that want to take advantage of that aspect of the systems as well. I mentioned a minute ago that we have a granite looking finish that can be incorporated into the Eaves system. It gives that sparkly look where the sun reflects off those metallic flakes that are contained within the finish to give it that granite look. I hope the picture is doing some justice. These buildings always look a lot better in real life than they do in photographs. Even brick. Eaves brick is very easily replicated in an Eaves finish. So that what you're looking there is an Eaves system with a brick finish that is not actually brick veneer or masonry on that particular building. Those are just some of the different finishes. There are many more that are available commercially out there in the marketplace, offered by different manufacturers, and people should take advantage of using those other finishes and having their buildings look like anything other than perhaps stucco that we see all too often across the Canadian landscape. So that concludes the presentation. I would just like to very quickly summarize some of the points that I've been trying to make here today. Probably didn't do a very good job of it, but nonetheless, the one thing that I wanted to point out is as it relates to the building envelope, Eaves is vital to a well-functioning building envelope. It is an integral component of the environmental separation. Once again, keeps the rain out, keeps the heat in, stops air leakage, controls condensation, and of course resists fire depending upon the particular code requirement applicable to the building and any wall of that building for that matter. From a cost perspective, Eaves is economical compared to all of the commonly used alternatives, especially if we are doing an apples to apples comparison where the wall assemblies deliver the same thermal performance. Okay, very economical. As I've said several times throughout the presentation, cladding a building with Eaves makes that building both sustainable and resilient. And last but not least, Eaves is aesthetically diverse. In other words, it can look like many things, not just stucco. So with that, I would like to thank you for your time here today. I hope that you have found this information somewhat informative. And I would invite anyone who has any questions about anything in the presentation itself or any of the code-related aspects that I was unable to dive deeper into because of time constraints and once again, because I didn't want to alienate or confuse some members of the audience by doing a deep dive into any particular code-related aspect. These issues are best looked at from either a provincial perspective or in some cases also from a municipal perspective. And when it comes to retrofitting, as we know, most buildings are for the most part unique and individual, and they have individual aspects or needs that have to be addressed as well. Today's presentation did not afford the opportunity for a question and answer period. So I've come up with a few questions that I have been asked in the past in some of my presentations. So I just like to maybe to try to answer some of those questions, at least from an industry perspective, starting off with the insulation thickness itself. The insulation is the backbone of any EIFS system, first and foremost. The minimum, in accordance with that CANUL CS 716.1 standard that I referenced, the minimum insulation thickness for EIFS in Canada is 2 inches. The maximum insulation thickness will depend upon the fire testing that has been conducted by the individual manufacturer. For the most part, what we're seeing as far as a maximum thickness being used or specified is 6 inches, as we saw in the example that I showed for the Ken Soble Tower. That was a full 6-inch insulation, and it could be anywhere in between the 2 and 6 inches, or even beyond, again, depending upon what the manufacturer of the system provides or offers, and what they have tested for as well, especially when we get into those fire-related tests that I touched on. As far as the use of which system is more appropriate, especially for the retrofit market, because we have buildings that are, for the most part, that were built to different standards at different times, depending on the code requirement may have been at the time the building was constructed. So now we've got a decision that many builders are faced with as to whether I should use a combustible cladding, or whether I can use a combustible cladding on my occupied building, or whether I must or should go to a non-combustible solution as they used on the Ken Soble Tower. And the only thing that I can say, once again, unfortunately, as with many of the things that I've said here today, it comes down to individual code requirements. And that's where provinces, number one, differ from one another. And perhaps even when it comes to this particular topic, it could also come down to the municipalities. There may be municipal requirements above and beyond what the individual province requires. And then, of course, it could depend on things like, was the building sprinklered? Or is that part of the retrofit strategy? So again, it has to be looked at from a holistic approach. Again, there are consultants that specialize in this area of expertise, and they should most definitely be consulted as to the appropriate solution for any given building in any province or in any climate zone for that matter. As far as the thermal performance requirements, once again, I didn't get into talking about specific R values other than to say that EIFS can deliver the full insulating value, the full thermal performance value of the insulating material, dependent upon, of course, the system and how it's detailed, et cetera, and that is more of a manufacturer specific issue. But then don't forget also, because there are different provincial requirements, we have many different energy codes across our country. Unfortunately, it is not a one-size-fits-all solution, and especially once you take into consideration the different climate zones, even within a given province. So once again, that is something that is best assessed by a design professional who will not only look at the retrofit as far as what is proposed to be done on the building, but also looking at the building from a perspective of the existing. What is there in that building already as far as existing insulation and other strategic elements that are required of the building envelope? So again, holistic approach, hire a design professional who can look at the entire building and, of course, the entire wall assembly to determine the best retrofit strategy for that wall. The one other thing that I'd like to just touch on, again, related to thermal performance, that we're asked from time to time, because EIFS must, by code, include a drained airspace, which is on the backside of the insulation, people question the thermal effectiveness of EIFS when you have an airspace inboard of the insulation component. And the answer to that is a very simple one. And it all comes down to something called venting or versus ventilating. What we don't do with EIFS is ventilate that air cavity, because that would induce convection, which would result in heat loss attributable to the airspace. With EIFS, we only vent the lower extremities so that water can escape. Okay, so that's the big difference between EIFS and perhaps other retrofit strategies, and why EIFS does deliver and has proven to deliver through independent testing that it does, in fact, provide those values. Those are the questions that I thought of on the top of my head that I thought I would address here today. Once again, I invite anyone to contact me directly if you have further questions regarding EIFS in general or regarding our own products and materials. Please, by all means, feel free to reach out and contact me. And with that, I thank you very much for your time here today. Thank you.